All right, go ahead and ask your question.
So with add delete vertices, we have an initial size of like 5 5. So what would we be adding an entire row or column?
Yeah, you would just add an entire row and an entire column.
And it would have to go at the end, right?
Yeah, oh yeah, it goes at the end.
You just use that, because we're using vectors, you just resize it, right?
Right, +1.
Okay.
How about delete? This is the one that's going to cause you headaches.
It would remove an entire column or row and shift everything down.
Yeah.
With a
Do the row first. You want to move everything up. Remove that extra, resize that last row. And then you're going to have, like, if you remove 2, you're going to have this break where this is missing, but all this will be shifted up. Then what you need to do is find that column, shift everything over, and then delete the last column for every vector. You see what I'm doing? So if you need, for example, to delete 2, step 1 to delete it would be you have 0, 1, and this is the new 3 and the new 4, and then you'd still have regular 4 right here because you would copy everything up first, and then you'd copy this one up, and then you copy the one below it up as well. So you copy all those first. So that's step 1, and then you would delete this last row, sorry, delete the last column. And then you would do the same thing, but for the columns. Now you have 0, 1, you want to have 3, and then 4, and then the actual 4. So what would happen is you'd want to copy, let's see, this one over first, and then next, and then that one next. And then you delete the last row, or last column. All right? It's not just doing those 2 steps, just make it work. The point of y'all doing it this way is to show you why the downfall of adjacency matrices is trying to do this is hard.
So you could have at position 2, you could have vertices 3.
I feel like I explained this completely wrong.
If you're deleting 2, you move 3 into the second spot. So
If you're
when it
deleting
goes-
2, the first thing you do is you take all the values here and you move them up. Right? Or this is what I'm telling you. Move that up. You do that first, then you move this up. So that 3 has replaced 2 and 4 has replaced 3, right?
Yeah.
Then you delete that row, and now 3 becomes the new 2, and 4 becomes the new 3. Okay? Then you need to do the same thing in the columns, where you're going to shift this over. Make sure you do the 3rd one first before the 4th one. Shift that over, then you do the 4th one. Then you delete that, and then 3 becomes the new 2, and 4 becomes the new 3. All right?
So I guess what I was asking is when you access index 2 after you've done the deletion, you're really getting the values
Yeah.
from 3.
Yeah. Oh, yeah, that's what yeah. Do it that way, and we'll just keep it easy like that. Okay. Unless my lab tells you otherwise, because the other way is you just infinity out the whole row and column. That might actually be easier for you. Which would you prefer?
I mean, infinity out the whole row seems.
Okay, maybe we'll do that instead. We'll see what the lab does.
Let's do both.
Why not? Why not both?
Yeah, because we gotta learn it.
All right, traversing the graph. How can we traverse the graph? Here we go. So you could say it's like a binary tree, except that it might have cycles, and you might not be able to traverse the entire graph from a single vertex. Y'all see why that might be the case? Most common graph traversals. Hey, depth first traversal and breadth first. Have y'all seen that before?
Breadth.
Breadth. Have I not done breadth here before?
Breadth.
Breadth. Like you're breathing only with a D?
Breadth.
Yeah, there's a D in there. It's like bread, but now with TH, so it's breadth.
It's like bread with a list.
Yeah. That is how it's spelled. That is not a typo. Yeah, I know. English, right? Lame.
Who came up with? Who said that?
Well, since it's 3 consonants together, okay, that's actually okay in English. I take that back. It was probably Dijkstra.
What does that mean?
With the 3 consonants together?
No, like that word.
Oh, breadth?
Yeah.
So with depth, you're going down all the way to the bottom and then coming up. Breadth, you start and then you evaluate everything that you could next, and then you take all those, you evaluate everything you could next. So you're evaluating the breadth of each level, as opposed to depth where you're going all the way down. So breadth, wide, depth, straight down. Yeah, usually when you see a lot of computer science words that have extra consonants for apparently no reason, I'll tell you the guy you need to blame. And it's not.
More effective.
What do you mean, which is more effective?
Like which one is like better?
It depends.
Yeah, it depends. Like,
I can never spell his name.
Dijkstra?
Dijkstra. Yeah.
Edgar?
See how Edgar.
Man.
Okay, look at that. There's a J, a K, an S, and a T.
Completely now.
Yeah.
I bet you it's pronounced Dijkstra.
There you go. If there's a computer science word with too many letters, especially some extra consonants thrown
Well, I
in,
mean, look at his name.
it's this guy.
I completely understand.
Yeah.
Look at it.
He's from the Netherlands. They like to add little consonants here and there. Not saying that's okay. I'm saying that's wrong, but that's what they do. So a lot of things, especially Rotterdam. Yep. Yeah, computer science words. Oh wow, 02. Oh, it's been 15 years. Oh. All right, depth first and breadth first. So depth first traversal. How do we do this? Well, we're at a node. We mark it as visited. Do whatever we want to the node, and then for each vertex adjacent to me, if I haven't visited, recurse. This is a recursive
If
algorithm.
you
Yeah, if it's not visited.
It's funny. This is what you was telling me at the competition.
Yeah, this is what you were using, right?
Yeah.
All right. What you should have used instead is the breadth first traversal. You're you're going in by each level, similar to traversing a binary tree level by level. Nodes at each level are visited from left to right. You start at the first index, the graph is traversed as much as possible, then go to the next vertex that's not yet visited. You use a queue to implement this. This makes a lot more sense with pictures. So depth first. If you are starting at 0, you go 0, 1, 4. You can't go anymore, so you come back up. You go 3, 2, 5, and let's say you went to 7. You can't go anymore, so you pop back up. Then you go to 8, and you can't go anymore. You pop all the way back up, and well, you haven't visited 6, so you're going to visit 6. You've already visited 4 and 7, so you're not going to visit those again, and then you visit 9. All right? Breadth first, you start at 1. You visit all of its children that haven't been visited, so then you visit 1 and 3. Then you visit all of those children that haven't been visited, which is namely 4 from 1 and then 2 from 3. Then you visit all the children that you can, which is currently just 5. Then you visit everything else. Well, you can visit the 7 and the 8. And then you try and visit those children, but they don't have any, so then you just do 6 and 9.
How does it determine which one of its children it goes to first?
What they're doing here is they're going with the lower number first.
Okay.
I don't think this picture actually explains it too well, so let's see if I can give you a better one.
How does it determine after, like with the leftover numbers, how does it determine which one to go to first?
It uses a queue,
Oh, okay.
and I'm going to show you that up on the board. All right, we got 0. Let's give them 1, 2. It's going to look kind of like a tree, but that's okay. 3, 4. Put a 5 here. 5 can go to the 4. That sounds great. The 3 can go to the 5. I think this is going to showcase it pretty well. Okay, how do we do this? You create a queue. You know what's funny about this word? How do you say that word without the queue? Thank you.
I pronounce it quay.
Thank you, David. So we're going to put 0 on the queue. All right, he's in the queue. We're going to evaluate the first element of the queue, which is 0. So we go to 0. What are the children of 0? Have we visited them?
No.
No. So we actually need to put a little visited data structure. Visited. So we visited 0. We haven't visited 1 or 2. So we're evaluating 0. So we take it out of the queue. We're going to put 1 and 2 into the queue. All right. Are there any other children? No. So we're going to go back to the queue. We're going to take the next element, which is a 1. We're going to mark it as visited. We're currently right here. Wow. What are its children? 3 and 4. Have they been visited? No. So we put them in the queue. We're done. We take what's next in the queue, which is a 2. Put them as visited. We add the children of the 2. 5. No other children? So we're going to evaluate the next element in the queue, which is a 3. We add its children, which is a 5. 5. But he's already in the queue, so we don't need to add him. So we actually don't need to add anything. We go to the 4. And let me just do this for the sake of argument. We go to the 4. Does it have any children?
Yes.
0. But has it been visited?
Yes.
So we are, oops, let me do this first. Take them out of the queue. We're currently in here. It's child 0. We've already visited 0. So we're not going to add it to the queue. And then next we go to 5. And 5's children is 4. Has that been visited? Yeah, so we're not going to add it to the queue. And then we go back to the queue's empty, we've done our breadth first search. All right, so that did 0, 1, 2, 3, 4, 5, in that order for breadth first, okay? Everyone good? Now we're going to do depth first. We start at 0, so we still need to have a little visited thing. We start with 0. We go to its first child, which is a 1, right? We go straight to the 1. We go to its first child, which is a 3. We go to its child, which is a 5. We go to its child, which is a 4. We would go to its child, but
We already have been.
all right, we've already visited it.
Visited it.
Yeah, that's not a queue. We're not using queue. Go back to the 5, no other children. Go back to the 3, no other children. Go back to the 1. We try to go to the 4, but
We already have.
already visited it, so we can't do the 4. We go back up to 0. Any other children?
Yes.
The 2, has it been visited?
No.
No, so then we go to
See, that was just so smooth. Yeah.
I'm glad you think the depth first is smoother. Which is more intuitive of these, actually? Breadth is more intuitive, which is probably easier to code. Depth. Which would you like me to code?
Brad.
Breadth. Definitely both, is that what you said?
We have to,
both
we
would be
have
nice.
to do both?
You're going to have to do both.
Brad.
Oh, yeah, definitely.
Oh, we were choosing those.
No, no. I'll code one, y'all get to code the other for the lab. Okay, great. So void, breadth, whoops. Breadth, first, traversal. And I'm going to be honest with you, I can never remember the syntax. It looks like that. Great, I'm glad. What is that?
Pointer to a function.
Pointer to a function. Okay, breadth first traversal. What's the first thing we need to do?
Instantiate a queue.
Here we go.
I was gonna say that.
What I said. I was yawning at it. It came out.
Actually of ints, because we're going to be doing it of nodes. Okay. Just call it the queue. We'll just get rid of those last UEs.
That's fine.
Oh, let's do. No, we'll do the full.
We're just
Technically, that was technically K.
Okay. Okay.
Okay.
All right. What's the first thing we add? Oh, actually, what else do we need to do?
Something with our visit function?
Yeah. What data structure should we do for visited stuff?
Okay. Vector.
We do a vector. What would be more efficient than a vector?
All this. Set.
Yeah, there we go.
The set that I have used.
I think we talked.
I
I think we've talked about sets, haven't we?
think we talked about it. We haven't used it for a lab.
Oh, okay, we're about ready to use a set for a lab. Sets are very efficient for adding and finding out if you've added it already. Traversing, not so much. But yeah, for what we want, be great. All right, so what's the first thing we add to the queue?
Whatever. Don't we start? First name.
Oh, hold on a second. I never remember the syntax. Good old Dijkstra.
And computer parts on Newegg.
What's that?
Are you looking at computer parts on Newegg?
I have. Oh, I did a presentation for ACM about building a computer, so I showed them what.
Black Friday deal's coming up. Is that Monday too?
Okay.
And upgrades.
So we can push, insert an element into the queue. Great. Dot push, which one are we pushing? 0, right?
Yeah.
All right. So we start our breadth first with a while the queue is not empty. So we're going to keep doing it until the queue is empty. Okay? First visit the node. Actually, we're going to do it this way. We visit the node first. And actually, these two could be switched. Add node to the set of visited nodes. And then lastly, we add all nodes to the queue that have not been visited. All right. Everyone good so far? Okay. So visiting the node, what do we do? Well, we just call visit on. Oops, actually we have to get the node. Hint node equals queue dot pop. Then we visit the node. Let's make sure all this some of the syntax is working correctly. So let's go ahead and create another test. Test, we'll do breadth test. Actually, we want to open it over here. And we also need to give it a function. So let's do void print constant int node. Ooh, we're going to do printf. I'll do that instead. That way we can give it a function. Now we can dot, was it? breadth first traversal. Print. Here we go. Let's see if that compiles. Void value not ignored as it ought to be. Oh, because pop actually pops it. What we want is what's on the front. So
you gotta do front and then pop it?
yeah. And I don't know if that's a function or a member variable. It's a function. Great. Good.
You also do peak.
That's Java. Yeah, that's Java. Okay. So that's good. It printed the first one. So we got that started. We did the visit. So we're going to add the node to the set of nodes. So now we're going to go is visited dot is it insert. Now we got to do this again. C++, STL set. I've probably looked at this. It's probably insert. Insert the element. Wait. Insert the node. So that's inserted. Add all nodes in the queue that have not been visited. All right. How do we do that? I erased the data structure. But what was our data structure? Let's see. Looks like this over here. So we're starting at 0. Which nodes should we be adding? All the ones that have not been visited. Well, we're doing breadth first, right? Don't look at this picture. We're now looking at that adjacency matrix. This is not what's on the board. We're evaluating node 0, which is this guy, or vertice 0. Which nodes or vertices should be added next? 3 and 4. Why is that?
Is that weights to them?
Because they have weights to them, which therefore mean that they have edges. All right. So to do that, find the edges that have weights and add them to the queue if you add them to the queue if what?
They haven't been visited.
If right. Haven't been visited. So for int I equals 0, I is less than m graph sub node dot size I plus plus. If, let's see, I does not equal node and m graph sub I is not visited, so is visited dot, what do we have? Oh, that's, oh, we have to do it that way. STL. Is visited dot find of m of the let's see, whoops, of m graph sub node sub I does not equal, wow, this is going to get confusing. Searches container for an element equivalent to val, returns an iterator to it if found, otherwise it returns set, comma, colon, end. Does not equal std set sub, what is the set of? Integers, end. We're going to make these each one line.
That visited is still wrong.
Thank you. And what's the last thing? Actually, that might be it. Oh, that's a, actually before then we forgot the middle one. Is greater than -1 if it actually has a weight to it. So don't add self, must have a weight must not have been visited. All right. Then if it satisfies all those things, q.add, is it mgraph sub node sub I. Okay?
We could queue push.
Thank you. Push. All right. Who thinks we got it? I hope so. C++ decided to have a different discussion about our code. Error, no matching operator. Yes. Sub node sub I has to be greater than 1. Y'all see that? Okay, good. Oh, good, only one error. Error, invalid use of non-static member function. Oh. End is a function, not a member. Wait, is it? Actually, this is what they mean. In is visited dot end. There we go. It's not equal to the end. All right. Ooh, stopped at 0. Whew. I++, I is not equal to node. Must have a weight. And we're actually saying if it is at the end, meaning it's not in the set. Segmentation fault.
Oh, yeah.
Yeah.
3 times.
Well, we got 0, 17, and 11.
But then when it went down,
Yeah. Wait, 17 and 11. What's going on here? Should be printing off 17? What should be printing off instead?
it should be printing off the position.
Right, not the 17, yeah. So we're not supposed to be adding that. We're just adding I, which is the node. All right, let's see what that does. Oh, there's an infinite loop.
Oh,
0, 3, 4, 2.
wait.
Yep.
Is it because you're pushing it on back to the queue?
Yes. What happens if it's in the queue?
Then it's just keep pushing it and then the
Right.
bot-
So we need to also and q, or not q, yeah, q dot find of m graph. Actually here we need to add I itself. Whew. We need to look for I. We're looking for the node if it hasn't been visited, and we try and find if the element's already in the queue. That's one way to do it. I'm going to tell you a simpler way to do it because this if statement is very confusing. Get the node, if is visited, find, oops, this is the easier way to do it. Find of the node, oops, we already visited it, continue on. Don't do the rest of the loop. Just go back up to the top of the while loop. This is going to be a lot easier than trying to call dot is it in visited down here. Just makes it a little easier. Also, you need to actually type this out correctly, where you say does not equal is visited, or yeah, dot end, aka it's already been visited.
Wait, yeah, it has to get it.
I want that word to have that S there, okay, man? Visited. 0, 3, 4. All right, now we're almost there. Why did we only print off 0, 3, and 4?
Because it's only evaluating the first.
One index.
Okay.
Needs to
So we needed
All
to
the
evaluate.
indexes.
Well, the problem is you jump down to 3, it goes back to 0, but that's already been visited. You go down to 4, you go back to 3, that's already been visited. You can't get to 1 and 2 from 0.
Oh.
Oh.
All right, this is where it gets also a little tricky and this loop becomes absolutely obnoxious. Now, if the queue is empty, check if there are other nodes that we need to add. All right, for int I equals 0, I is less than mgraph.size, I plus plus. I'm going to say I represents the node slash vertex number. Remember using node and vertex interchangeably. If is visited dot find of I equals is visited. Whoo! Oh, I did it over there too.
And the other one.
Man, it's just not a good day. Then we need a queue dot add or dot push, sorry. Dot push I. And let's also make sure this for loop ends by saying and queue dot empty. So you keep going while the queue is empty. If you find something that we need to visit,
Yeah, add a Y.
queue, then you go and you add it. All right, let me make sure that's right. Now if the queue is empty, and you find something, push it back on. Great. There we go. Now I went to the 1, tried to add something, but it's already visited 0 and 3 and 4, so then it just went back to the 2. All right. So breadth first has a lot more coding to it because you can't just give a simple recursive definition. But in general, it's actually more efficient because you're not having, well, for what you're doing, it's generally more efficient because you don't have to go down the full list of everything. All right. How are we doing? Oh, perfect. Because this is right where we need to stop. What was that? Oh, I lied. We need to do shortest path.